This study was a collaboration with colleagues at KIT in Germany and the University of Saskatchewan in Canada. Recent studies have shown soil relative gas diffusivity to be a good predictor of N2O emissions when comparing soils of varying bulk density. It's also recognised that the site preference of N2O, which is a descriptor of the isotopic arrangement of the N2O molecule, can be diagnostic of denitrification processes. Thus, this study aimed to examine the relationships between N2O fluxes, soil N2O and oxygen profile concentrations, and model gas diffusivity. And we also aimed to examine the relationship between N2O site preference and soil diffusivity. Repacked soil cores were saturated and a nitrate solution was applied before soil cores were drained in a stepwise manner. At each drainage step, N2O fluxes and soil N2O and oxygen concentration profiles were measured, with soil gas diffusivities calculated using the model of Muldrow et al. The relationship between N2O site preference and soil gas diffusivity was examined using published data sets of water-filled pore space versus N2O site preference, and modelling the soil diffusivity from the data provided. Figure 1 shows how increasing airfill porosity over time, with increasing drainage, causes relative gas diffusivity to increase exponentially. In Figure 2, we can see that once the soil diffusivity exceeds recognised anaerobic boundaries, the N2O fluxes rapidly decrease. This is reflected in what is happening within the soil profile of these cores, as shown in Figure 3, where N2O production is inversely related to soil oxygen concentration. Comparing published N2O site preference data with modelled relative gas diffusivity in Figure 4, we see a clear decline in site preference towards values recognised as defining denitrification when soil gas diffusivity drops below recognised anaerobic limits. So in summary, this study shows that the onset of denitrification derived N2O can be determined by considering modelled values of soil gas diffusivity.